Thank you. Thank you. It's really glad to be here. Actually, my second time to be in this institute. The last time was a few years ago, but it was a workshop. I think that's before COVID, for sure. 2018 or 2019, I don't remember. Okay, so because I don't really know the background of the students, first maybe let me just ask how many are experimentalists? Or okay, and you're working on which experiments? RCB? How many RCB? And Bell? And then what experiments? JLab? Okay, good. Then I assume probably you don't know very much about this heavy exotic stuff because that's not really the focus of Bell. And are there any postdocs or? So most are graduate students. So my name is FENG KUN GUO. I come from Institute of Theoretical Physics, belonging to Chinese Academy of Sciences. So this is really, just like Max Planck Society in Germany. It's kind of that stuff in China. It has more than 100 institutes. And ours is probably the smallest one. We only have something like 40-something faculty members. And I have teaching assistants here. They will also help Juan for his tutorial. This is my former students, Teng Ji, Miss Teng Ji, and Mr. Xiangkun Dong. So they are now postdocs in Bonn. So if you have any question, just ask, just pause me, and ask questions at any time you want. Okay. So I think will there be any break during these 2 hours, or I just continue up to the end of? Oh, okay, good. Okay, I can do that. So, so I will start from because the lectures, both mine and Juan's lecture, focusing on the exotic hadrons. Okay. Can you see this clearly from the very end of this classroom? Good. I use my favorite chopstick. Okay, chalks. Yeah, I took this from China, and so I always use this. Okay, so I will mainly focus on the meson stuff, and Juan will talk about this baryonic stuff. But first, let me just introduce what are exotic hadrons. Okay, so I assume that you are all working on hadron physics, so you know all this basic stuff. But then to define what exotic hadrons are, first we know that the normal hadrons, the conventional hadrons, they are just a QQ bar quark anti-quark pair for meson, and just three quark for baryons. And then all these hadrons beyond this kind of configurations, we call them as exotic hadrons. So from this point of view, you see these exotic hadrons are really something defined in terms of quark model picture, okay? But then there are some kind of features that we can really distinguish exotic hadrons from the conventional hadrons, or the normal hadrons, and what they are. So the first ones, let's focus on the meson stuff. And then we need to know the features of the normal mesons from the quark model, from QQ bar, right? Which are the conventional mesons. So they have a certain quantum numbers, okay? But the quantum numbers we call the spin. So I will start from the very basic stuff. And also, most of my lectures, actually, I will talk about these ideas and qualitative understanding. For very tedious derivations, you can ask the teaching assistants. the difficult tasks are for them. So this is spin, this parity, this is C parity, right? Now we want to know what kind of DPC quantum numbers for a pair for quark anti-quark meson. So now we consider, for instance, a meson. We have a quark here. We have an anti-quark here, right? We just put them into their rest frame, x, y, z. And this one has a coordinate of r. And this guy, I put that coordinate minus r. It's not really, but you understand, okay, this minus r. So now I make, for instance, this the parity transformation. Parity transformation, then this just allows us to transform r to minus r, right? Okay. And then if we think of this, we put this r, this angle, this polar angle is theta. The azimuthal angle is this one. This one is phi. Okay. Now this parity transformation is this guy, and then this r, this theta and phi, will become what? Become pi minus theta, right? The polar angle is pi minus theta. And then the azimuthal angle would be this one, and then the other side is here. So it's a pi plus phi. Okay. Now you consider their wave functions, right? You make a parity transformation, and the wave function also depends on these angles. We have this angular momentum conservation, and then we can just define all these methods according to their angular momentum, orbital angular momentum. And we know this one is equal to minus 1 to the power of L, and then y theta phi, right? So this just tells us, making parity transformation, we introduce a factor of minus 1 to the power of L, right? And then quark, anti-quark, they are fermions and anti-fermions. So they have opposite parities, right? The anti-quark has opposite parity compared to the quark. And then we have an additional power of minus 1, so additional factor of minus 1. And then finally we get parity equals to minus 1 to the power of L plus 1. Okay, that's parity. So how about the C parity? Again, we put here as a quark and here as anti-quark. So what C parity does, right? It just turns this quark to anti-quark, and then this anti-quark to quark, right? So from here, immediately you see they will also receive this kind of factor, right? Because the coordinate of quark now becomes the coordinate of the anti-quark in their adjacent version, and then the anti-quark becomes quark. So it receives a factor of minus 1 to L plus 1. But that's not all, because they also have spins, right? Because spins, if you do this parity transformation, it does not matter what kind of spin you have. But for the C parity, you would have a different consequences. Because quark, anti-quark, they are spin will have particles, so they can form either spin 0 and spin 1, right? That's a spin, and the spin for quark, anti-quark, right? This is spin for quark, anti-quark. Now for spin 0, so you know their spin, the wave function in their spin space. So is that symmetric or anti-symmetric? Spin 0, you have two spin 1/2 particles. You form them to spin 0 combination. Their spin wave function, is that symmetric or anti-symmetric? Right, anti-symmetric, right? Quark, anti-quark, minus quark, anti-quark, right? Something like this. You have anti-symmetric for the spin wave function. And then for the spin 1, you have, of course, you have 3 different components, but then all of them are symmetric. For instance, we choose the one with the positive third component, right? This is symmetric, and this is anti-symmetric. Now we make a C parity transformation. A C parity transformation, and this Q becomes Q bar. This one becomes Q. Now this Q bar, Q, right? Because of the anti-symmetric nature, of this spin 0 wave function, and then we get a factor of -1, right? So we get for spin 0, we have a factor -1, okay, for the C parity transformation. For spin 1, because they are symmetric, so it does not really matter what kind of ordering you put quark, anti-quark. So you have a factor of +1, right? But -1, you can write this as -1 to the power 0 plus 1. And +1, you write this as -1 to the power 1 plus 1. So we can just rewrite these two guys as a factor of -1 s plus 1. This s means the total spin of quark, anti-quark, okay? This is their relative orbital angular momentum. So finally, we have the C parity is -1 L plus S. Okay? But you see, all these derivations, we assume what we consider is that the quark and anti-quarks, they are particles and antiparticle of each other. Right? This means for any meson, if the quark and anti-quark, they are not particle antiparticle, and then you don't have C parity. That kind of mesons are not C parity eigenstates. Okay. So the C parity eigenstates, they are the flavor neutral mesons. Flavor neutral mesons. Okay, what does flavor neutral means? Because this means they don't carry any net flavored quantum number. Right? For instance, you have UU bar, DD bar, SS bar, CC bar, BB bar. Right? So for instance, then for pi plus, and then the pi plus is UD bar. Right? This guy does not have C parity. Right? Although you know this belongs to the 0 minus plus meson octet, but this guy does not have C parity. It's only the pi 0, pi naught, it has a C parity. It's a C parity eigenstate, and the eigenvalue is +1, right? Because this S with meson and the total spin of quark anti-quark pair is 0. So pi minus, this is D bar U or U bar D, okay? These guys are not C eigenstates. Okay. We will talk about this a bit later. Now, we form all possible parity and C parity from a pair of quark anti-quark. And now we can list all possible GPC combinations for QQ bar pairs. Okay. We consider, for instance, spin S equal to 0 and S equal to 1. We consider these two different groups. Okay. This S means the total spin of QQ bar. Now, the total G, that's S and L. So the G is formed by the total spin and the orbital angular momentum. So we consider, for instance, the L equal to, okay. So, okay, this one is simple. So S equal to 0, and then we have parity equal to -1 to the power L plus 1, right? Because S equal to 0, and then this L equals to G. Then it's -1 G plus 1, right? And then the C parity is -1 L plus S is -1 to the power of L, or -1 to the power of G, right? In this case, L equals to J. So what you have would be the GPC equal to, for instance, we have odd spin, odd J quantum numbers, and then the parity would be what? Positive, right? for odd G, and the C parity would be negative. Okay. And then if we consider even G, and then this parity and C parity would be just the opposite to the previous case. Okay. And then we have these combinations, right? And then for S QQ bar equal to 1. And then now we consider the combinations or the coupling of the total spin and the orbital angular momentum. Now first, we consider, for instance, L equal to 0, the S wave ones, right? That's S wave, okay? So we use this nomenclature. This S wave means orbital angular momentum 0, and the P wave, D wave, F wave, and so on. Okay. For S wave, and then what we would have is G equals to 1, right? G equals to this 1 and 0 decoupled to 1, and then the parity and the C parity. What are the S wave mesons with total spin 1, right? That's for instance the rho, the omega, the phi. Their quantum numbers are 1 minus minus. This given here. And then for L equal to 1, that's P wave, right? The P wave, and this one we couple the orbital angular momentum, total spin, and what we would get. The total angular momentum of the whole system, or the spin of the meson, would be, we have 3 possibilities, right? We have 0, 1, 2. One couples with another one, we get 0, 1, 2. This is 3 possibilities. And the parity would be -1 to the power L plus 1, positive. C parity would be the -1 to the power L plus S, again, positive, right? And then for L equal to 2, D wave, okay? You would have the spin of the meson, or the total angular momentum of the QQ bar system, would be 2 coupled with 1. We get 1, 2, 3. This is 3 possibilities for the spin of the meson, right? But now, the parity is -1 to the power 2 plus 1. That's negative. And then the C parity again is negative. Right? You see, for this kind of set, the parity is always equal to C parity, right? And you have this kind of possibilities, and then you will find this line and this line. They do not exhaust all the possibilities, right? Then you have certain quantum numbers that you cannot form from coupling quark to antiquark. These are called exotic quantum numbers. This means as long as you find some meson or some kind of a resonance with this kind of exotic quantum numbers, and then you know for sure this, once you confirm this is really hadron state, and then you know for sure this corresponds to exotic hadron or exotic meson that cannot be formed from a quark-antiquark pair. And then you see what I'm missing. Okay, what I'm missing. There are infinite possibilities I'm missing, right? Immediately you find 0 minus minus is not here. There is no 0 minus minus. There is no odd minus plus. And there is no even plus minus. Okay? These are all exotic quantum numbers. You cannot form these quantum numbers from considering simply quark-antiquark pair. And of course, experimentalists or have tried to search for the states with this kind of quantum numbers. There are not much success, but there are some evidences. For instance, there is one called pi 1, 1400, or there are also some kind of evidence for pi 1, 1600. So what does this name mean? So you will see there are many names of different hadrons. And then this names means, this pi means this is azimuth spin 1, PC equals to minus plus states. Okay, pi 1 means our pi g. If this is pi g, and then this would be JPC equal to g minus plus. Okay. Pi 1 then means this is azimuth spin 1, JPC equals to 1 minus plus state. And there are some evidences for the existence of pi 1 with a mass is around 1.4, 1.6 Jeff, but so far there is no consensus what they are, and whether there is only one state or only a single state, or there are two. Okay, it's not really fixed. And also, 2 or 3 years ago, there were some new observation from basis 3 experiments. This tool has a long history, but this one is pretty new. That's reported by basis 3, I think at the end of 2022. I think 2022 could be. So this one, from the name, you can judge this one. The only difference in the quantum numbers compared to the pi 1 would be azimuth spin equal to 0. JPC again equal to 1 minus plus. Okay. So these are the exotic quantum numbers. Of course, these are the exotic quantum numbers only from the GPC quantum numbers. You can have certain other exotic quantum numbers. For instance, other possibilities. Okay, other possible or exotic quantum numbers. For instance, if you consider heavy quarkonium mass region, okay, heavy quarkonium like states. This means their masses are much higher than the normal light mesons. The light mesons, their masses are a few hundred MeV, 1 point something Jeff, or the very highly excited ones, 2 point something Jeff. If you have states with masses around 4 Jeff or even higher than 4 Jeff, and then you would not think that is the normal light meson, this kind of exotic state. And then you would think that would be containing some CC bar and components inside their wave function, and possibly more. If you have this kind of states, if they are charged, or if they have azimuth spin and strainedness, okay, non-vanishing, or does not equal to 0. Okay, and then you know they are exotic states. They are the good examples are the so-called ZC 3900. Okay, this was reported by basis 3 or Bell in 2013. And then these are charged. Okay, so you see this mass is around 3.9 Jeff, and they are charged. So they cannot be the normal light meson, because they are charged. Then they cannot be the normal charmonium states. And of course, later basis 3 also observed evidence or structures with 0 electric charge. And then the basis 3 also reported 4020, okay, plus minus and 0 later. These are in the charmonium sector. Before their observations, there were also observations by Bell. They reported ZB 10610 plus minus 0, ZB 10, 650 plus minus. Okay, 0. I just put. Bear on 2011. Okay. These are these exotic quantum numbers. But here, we introduced the C parity, and we see this pi plus pi minus. They belong to the same azimuth spin multiplied as pi 0, but only one of them has a C parity. This pi 0 has C parity, but pi plus pi minus, they do not have C parity, right? But all these 3 pions, they are in the same azimuth spin eigenspace. In the same azimuth spin or triplet, okay? This means their total azimuth spin is 1. Okay, we want to have kind of quantum numbers that the quantum number will be the same for all the mesons, all the members belonging to the same azimuth spin multiplied. And then what that kind of quantum number is, that was introduced by C.N. Young many years ago. That's G parity. Okay, C.N. Young is still alive. It's 100 something. This G parity. Okay, so you consider what you would introduce, right? For a kind of azimuth spin multiplied to have the same quantum number. You can think of that. Okay. For instance, now you have pi plus, pi minus. We put that in in some the third along the axis of the third component of azimuth spin. Okay. Now we want them to have the same quantum numbers. We do some C parity transformation. Okay. That's I azimuth spin the IZ, IY, IX. Okay. C parity transformation would just transforms pi plus to pi minus to pi plus. And now we want this guy under this kind of new transformation, the quantum numbers that we would like to introduce. This one needs still to be eigenspace of that new quantum numbers. But now with the C parity transformation, this one is transformed into pi minus. Okay, what kind of other transformation that we can do to make this one to become back pi plus? Okay, we can think. So we just make rotation in the azimuth spin space, right, along the y-axis, for instance. You can do this along the x-axis. Doesn't really matter. We just normally choose the y-axis. And then this we make a rotation of 180 degrees. And then this pi plus is rotated to here. Pi minus is rotated to above. And then with this combination of transformation, we would have a defined new quantum number, which is called C parity. That would be C parity and -1, or sorry, the rotation E to I on pi 180 degrees. We ask this to rotate along the y-axis, right? Operator. Okay. Now this one, if we define this way, we know this one. All the 3 pions should have the same quantum numbers, right? The same G parity, because pi plus, pi minus, they just transform twice, and then they have the same quantum numbers. Okay. Now, if we X this to, for instance, to a given state, I Z, right? So we X this to this state I Z. So then we can insert a completeness relation. Then I Z prime, I Z prime, and then we need to sum over I Z prime, and then E minus to the power of minus I pi I Y I Z. Okay. And you do this, you use the small Wigner D function. You do this, and you will find this gives you a kind of a factor. Okay, this gives you. Okay, I can write this. So it gives you something like -1 to the power I minus IZ, or IZ, something like this. So I don't do this step by step, but it gives you this kind of factor. Okay. Now we choose, because we see all the three members in the same R-spin multiples, they have the same C parity. We simply choose the one with 0 IZ, right? And then the 0 IZ, this gives you a factor of minus I. And then this gives you that G quantum number is -1 to the power I, then times C. And then it's -1 L plus S plus I, okay? So this gives you this formula, okay? The G parity is the C parity times -1 to the power of the R-spin. And from here, you immediately know the G parity or the pion, okay? Or pions is what? Pion Z parity is positive or negative? Positive or negative? Pion Z parity, pion C parity is positive, right? R-spin is 1. The Z parity is negative, so it's to the power of 1, and then you have negative Z parity. Now you can judge from requiring R-spin contribution, this kind of stuff, to see what kind of decays or what kind of reactions are preserved by preserves R-spin symmetry or the G parity, because we know the strong interaction. If we don't consider the so-called the strong interaction is always respects the C parity. So if we only consider strong interaction, and then C is conserved, then the Z parity conservation is equivalent to R-spin conservation. Okay. It's another easy way to judge whether reaction is R-spin conserved. Okay. So far, I have not talked about this the heavy hadron stuff. Okay, but these are just starters. So just to set up the stage that you know this Euro quantum numbers that we will use in this hadron spectroscopy analysis. Questions? Yeah, please. Okay, the +1, this one. Okay, that's because fermion and antifermion. Okay, if the parity of fermion is, for instance, eta p, then its antiparticle, the parity would be minus eta p. Okay, their parity are opposite to each other, because we have a quark and anti-quark, and then we have eta p times minus eta p is a factor of -1, and then this gives us this additional factor -1, and then we have -1 to the power L plus 1. Sure, yeah, because the parity of the whole system consists of 2 parts, right? Consists of the parity of each individual components, their product multiplied by additional contribution from the orbital angular momentum. This tells us that if we consider a system of 2 mesons or 2 bosons, the parity would be -1 to the power L without +1. Okay. Or if we consider 2 fermions without antifermion, then it's again minus 1 to the power L. Okay. This one is only for fermion, anti-fermion. But for the C parity, so for the C parity, actually, you see, if we consider two bosons, there is no this factor. And then again, there is also no this +1 factor, because you consider the coupling of two integer quantum numbers. Okay, and you will see the combination is opposite, is different from the coupling of two half integer angular momentum. So this one holds for both fermion, anti-fermion, and boson, anti-boson system. Okay, for both fermion. Okay, I simply write F bar, fermion, anti-fermion, and boson, anti-boson. Okay, this one. And this minus 1 to the power L plus 1 holds only for fermion, anti-fermion. And for boson, anti-boson, and there is no this +1 factor. Any other questions? If not, then I will start with the heavy quark stuff. Okay. Of course, for this for this quantum numbers, I guess Juan in his lecture about chiral symmetry, he will use the quantum numbers, because this will gives you the quantum numbers of the spontaneously broken, the Gaussian bosons resulting from the spontaneous breaking of chiral symmetry. Okay, so let me start with the heavy quark stuff. For the heavy quark stuff, okay, I will focus on the symmetry related consequences. Okay, these are the heavy quark symmetry. I put this as a plural because there are different kind of heavy quark symmetries. So we know the QCD. What kind of symmetry does QCD have? So it's the symmetries of QCD, right? So our starting points are the symmetries of QCD. They're either exact symmetries or approximate symmetries. Okay. Of course, we have a Lorentz symmetry, Lorentz invariance. We have a color, right? The color is conserved. And then we have some other symmetries. For instance, the parity or transformation. Well, we have a C parity transformation, C parity, or the charge conjugation, okay, charge conjugation, and in QCD there is a so-called theta term, which is irrelevant to our discussion. I simply forget about that. And then the QCD would have parity and CP, or time reversal, right? Time reversal. And we know for any local quantum field theory with Lorentzian invariance, the T is equivalent, or CPT is always conserved, and then this T is equivalent to CP. Okay. We have this kind of exact symmetries for QCD. And then we have approximate symmetries. These are exact. And then we have approximate symmetries. Approximate, okay? So these are exact symmetries. So the QCD Lagrangian is exactly invariant and all these transformations. And then there are approximate symmetries. When we'll talk about this light guys, this chiral symmetry, which is approximate. That's for light quarks. This light. This means we consider limit that these light quarks sending their masses to 0. And then we have the heavy quark symmetries. I would write these heavy quark symmetries. Okay, heavy quark symmetries. These are approximate symmetries that we would obtain if the quark masses are infinitely large. Okay, if the quarks are infinitely heavy. Okay? So it's simply an opposite limit that you would learn from the next lecture. Okay? So, of course, one can derive these symmetries from the Lagrangian. We just make do some mathematical treatment, and we would be able to derive this. But we will not do that. So we simply argue with wordings. Okay, this QCD should have certain heavy quark symmetries. The first one we would consider is heavy quark spin symmetry. HQSS. Okay. Actually, it's very simple. It's just like your interaction of some spin, some particle with a spin with the electromagnetic field. Right? The particle with a spin, you put that inside the electromagnetic field. And what would the interaction would be? What would be the interaction? It's the interaction through the magnetic moment of that particle with the spin field, right? You have a magnetic moment. It interacts with the spin field. And then your magnetic moment is proportional, of course, to the charge. And then it's the most important stuff is anti-proportional to the mass of some and then interact with magnetic field. It's anti-proportional to this guy. Okay, but what is magnetic field? Bi, right? So this is if you think of in terms of this field strength tensor, right? This what is this one? This is epsilon I jk partial g a k, something like this, right? This is your vector potential. That's a derivative. Right? This is your magnetic field. So this means your magnetic moment interacts with, for instance, a photon, and then the interaction strength is proportional to the momentum carried out by the photon, right? Some particle with a spin interact with photon, okay? And then the interaction strength would be anti-proportional to the mass of this guy. Of course, also spin is somewhere, okay? Okay, I think I simply write in this way. It's a spin I neglect. And then it's proportional to the momentum of this photon, momentum of the photon. And then this is momentum P, or that's momentum P prime. And then this would be, the photon momentum would be P prime minus P, something like this. Okay. So as long as the momentum carried out by the photon is more, and then the interaction with magnetic field, or the interaction that involves the spin of the particle is small, right? So this means if we send the heavy quark mass to infinite, this guy is simply suppressed. It's simply goes to 0. The spin dependent interaction, I would put this V or spin This simply goes to 0. Okay. Of course, we need to know whether this kind of condition that the momentum carried out by the photon is more, whether this holds, right? Of course, we do not really care about photon. What we care is in QCD. So we care about the gluon, which is a QCD analog of photon. So all hadrons, they're formed by the quark, antiquarks, and the gluons. And then what we would have is this hadron, and this quark, it interacts with the gluon. And then the momentum carried out this is a gluon momentum, right? But how large is this gluon momentum? So if we consider hadron with heavy quarks and light quarks, consider heavy, light hadrons. What would be the typical momentum carried away by exchange gluon? So the quarks, antiquarks, they all confined inside the hadron, right? We have a confinement. Confinement is completely non-perturbative stuff of QCD. Non-perturbative QCD, right? And then we have energy or momentum scale for this confinement for this non-perturbative QCD. Well, that is the so-called lambda QCD, right? Which is a scale that your QCD, your strong interaction, is completely dominated by non-perturbative interaction. Right? Thus, we have the lambda QCD. That would be the order of 300-400 MeV. Okay? So for all hadrons with a heavy quark, and then others are light quarks, and then the gluons, because they are all confined inside these hadrons. And then all gluons, they should have this kind of energy momentum scale, right? And then this guy, the proton, the momentum will be order lambda QCD, okay? And then the spin dependent interaction would be proportional to lambda QCD over MQ, okay? And then we would have for this Q to be charm quark or to the bottom quark. This is a good approximation because the charm quark mass is 1.2, 1.5 Jeff, so larger than 1 Jeff. So this one would be lambda QCD over MQ would be around 20% or 30%, 20 to 30%, right? So we have a good approximation. So for us theoreticians, 0.3 is a small number. 3 is a very large number. There's the first approximation, 3 is infinite. 0.3 is 0. So you know the value of the unit electric charge. What's the value in natural units? Alpha equal to E squared over 4 pi. What is the value of E? Compute this. And then for bottom, lambda QCD over MB is much better, right? Because MB is 4.5 Jeff, and then you would have something like 10% or even smaller than 10%. So there's a very good approximation. That's a moderately good approximation. So we have, this means for hadrons with a heavy quark and others are light quarks, we have very good approximations for neglecting the spin-dependent interactions. How about heavy quarkonium? Okay, for instance, purely or heavy systems. Now the momentum scale is not set by a lambda QCD, because now you have different stuff. For instance, we have QQ bar. Okay, the momentum scale is different now. So what the momentum scale is for this one? The momentum scale. So you consider, for instance, if you consider a very, very heavy quark, and then at some point this quark anti-quark, they would be very close to each other. That's because if for instance you consider hydrogen, the size of the hydrogen is the Bohr radius, right? The Bohr radius is basically the inverse of the binding momentum, right? Inverse of the binding momentum. Binding momentum would be the reduced mass times the velocity. Okay, I would write this approximately equal. Okay. And the velocity, how large is the velocity? You will find this velocity is for leading order. You only consider the one photon, one gluon exchange. The velocity is basically alpha or alpha-s. Okay, we have very heavy systems, and then this guy becomes very large. At some point, the whole stuff becomes a very large energy or momentum scale. Large compared to lambda QCD. It's a very large momentum scale. And then the size of this QQ bar becomes small. And then because they are small, this actually only happens when your MQ is very large. But still, your V, the size of V is around the order of alpha-s. So this means in terms of if you check the value of alpha, the strong coupling constant, at some point, for instance, at 1.5 Jeff or 3 Jeff or this kind of stuff, your alpha-s point something, right? It's for instance, for heavy quarkonium, for ground state CC bar, your alpha-s or your V, the velocity of your heavy quark, is, or the velocity squared, is around 0.3. And then for BB bar ground state, you would have VQ squared around 0.1. Okay. So this kind of analysis comes from that we neglect all confinement stuff. Right. This all is just analog of hydrogen or positronium. But why can we neglect confinement? That's because for very, very heavy quark mass, and then this guy becomes large, and then at some point, the size of the system is so small, your van Gogh exchange becomes more important than your confinement, because confinement, the linear potential is proportional to the radius, but the Coulomb interaction, the color Coulomb interaction from the Gogh exchange is anti-proportional to this. So when you have very small r, and then the system is dominated by this guy. And then for this system, confinement is not essential. But the van Gogh exchange is very important. But still, the velocity is small enough that you can use this as, or that you can still use the heavy quark, approximate heavy quark spin symmetry, because now the momentum scale of the gluon carried away from heavy quark is mv multiplied by vq, and then this divided by mq. Again, you would have something like vq, which is against still a small number, although now it's v squared is 0.3. Okay. So we have heavy quark spin symmetry. Yeah, I think so. Then we have a break for 10 minutes. If there are questions you can still ask. So any questions? So you can ask questions anytime, okay? Or if not, I think let's just start the second hour for today. So here, just to introduce the concept of heavy quark symmetry. But then we should have some kind of consequences, right? Yeah. No. This is not. Okay, so for Gaussian boson, that's kind of spontaneously breaking of continuous symmetry. Here, this is not spontaneous breaking. It's just approximate symmetry. It's not a spontaneous breaking. Right? I think because for symmetries, we have different kind of realizations. We have the so-called Wigner-Well realization. Then all the spectrum, they will have the same symmetry as your Lagrangian. And then we have a Nambu-Guston boson, Nambu-Guston realization. And then symmetry is hidden, or the Lagrangian has symmetry, and then the spectrum does not have that symmetry. For that kind of stuff, you would have a Gaussian boson or the pseudo Nambu-Guston bosons. But here is the Lagrangian has the symmetry, and also the spectrum has the symmetry. And also, this is not kind of continuously rotation, this kind of stuff. So now we want to explore consequences of heavy quark spin symmetry. Okay. For this, so we know the orbital moment, the angular momentum is conserved. Angular momentum conservation. But this angular momentum, this consists of two parts, right? Consists of the heavy quark spin and all the rest. Okay? I simply write this as SL. This SL means the angular momentum of the light degrees of freedom, which is normally called in this way. Or sometimes it's called, for simplicity, spin of the light degrees of freedom, angular momentum of the light degrees of freedom, okay? Which means light quarks, light antiquarks and gluons, and also the orbital angular momentum. Okay, this is sum of all the quark spin quarks plus sum all the gluon spins plus orbital angular momentum. Okay? So this one really contains both spins and orbital angular momentum. Now, we see the heavy quark symmetry in the heavy quark limit. The heavy quark spin does not interact at all, right? And then this means this guy does not play any role. Although the heavy quark has a spin 1/2, but its spin does not play any role in the dynamics, right? We call this simply decouples. Okay? So it does not really matter whether your heavy quark spin polarization is polarized upward or downward. It doesn't really matter. Your system will not be sensitive to the polarization of the heavy quark spin. As long as the momentum scale is much smaller than the heavy quark mass. Okay? And then this means the rest, this guy would become a conserved quantum number. And then this SL, it becomes a good quantum number. Okay. This is a concept. Of course, in the limit that heavy quark mass, sending heavy quark mass to infinite. So we know for a good quantum number, and then this means it commute with the Hamiltonian, and then all these Hamiltonian eigenstates would have also would be also eigenstates of this good quantum number, right? This means we can classify hadrons containing heavy quark according to this quantum number, right? So we have a heavy quark spin symmetry multiplex. Hadrons, heavy hadrons, within the same heavy quark spin multiplex, they have the same SL. For instance, we consider the S-wave heavy light mesons. Okay, heavy light mesons. And then S-wave means the orbital angular momentum is 0. Okay, and then the SL for this S-wave heavy light mesons would be simply the spin of the light anti-quark. That's 1/2, right? For S-wave heavy light mesons, the parity of the meson is what? For S-wave, it's negative, right? We just talk about the parity. So this 1/2 minus. Okay. So what are the mesons that we have? The familiar mesons that we know. These are the D star, right? Both D and D star, they are S-wave charm mesons. The only difference of these two mesons is the heavy quark spin, its alignment with the heavy anti-light quark spin, right? The only difference would be the heavy quark spin polarization directions. Okay, so these two guys, they become degenerate in the heavy quark limit. So they are in the same heavy quark spin multiplet, or sometimes they are called heavy quark spin doublet. Okay, and then we have B and B star. Okay, so this is a heavy quark spin multiplet. This is another heavy quark spin multiplet. And if we consider baryons, so Juan will talk about baryons, but probably let me just set some foundation for his lectures. And then heavy S-wave baryons, Q bar, okay? Capital Q, the heavy Q and the light Qs. For instance, the QQ, we consider UD, okay? And then this one we consider C. And then we have different heavy the charm baryons. Then we have sigma C, right? We have lambda C. Okay. So now the question is, what is the SL value, the angular momentum of the light quarks in this system would be this the two light quarks, this system. What would that be for sigma C? What would that be for lambda C? Okay. And then how can we decide on that? So the U and D, they are within the same isospin multiplet for quarks. And then if we consider isospin symmetry, U and D, they are generalized identical particles, right? They are within the same isospin multiplet. And then they are fermions, and then they must obey the Pauli principle, or the Fermi's Dirac statistics, right? Their wave function must be totally antisymmetric. So their wave function contains several parts: color, spin, flavor, and the coordinates. Okay, I put that as R. Okay, coordinate space. For color, so what is the color wave function for baryon? Any baryon is a color singlet, right? The color singlet, to form a color singlet for 3 quarks, the only possibility is this. So if I assume you all know group theory. So this is from group theory. And then this means in the same column, all these quarks, they are anti-symmetric in color space. So this anti-symmetric, okay? I use this A to represent anti-symmetric, okay? And then it does not really matter whether this is lambda C or sigma C, they are all anti-symmetric. And then we consider S wave, and then for the coordinate space wave function, they are symmetric, okay? And then that's for U and D, right? We consider the total wave functions for UD system. And then the combination, the products of the spin and the flavor wave functions for both states, they must be symmetric, right? Here is anti-symmetric, here is symmetric, symmetric, and then their product must be symmetric. This means one of them, for instance, if a sigma C, there's azimuth spin 1, right? This is azimuth spin 1, and lambda C is azimuth spin 0, heavy baryon, okay? Azimuth spin 1, for azimuth spin 1, and then what is the flavor wave function? The flavor, azimuth spin is a flavor symmetry, right? For azimuth spin 1, the flavor wave function is symmetric or anti-symmetric? Yeah, please. Symmetric. Yes, this is symmetric, right? And then what would be this spin wave function? And then from here we would know, of course, this must be symmetric. Right? A symmetric spin. This means the total spin of the two quarks would be SL equal to 1. Okay. So the total spin of the UD quarks inside sigma C must be 1. And then for lambda C, it's different. It's opposite to the sigma C, because for lambda C is azimuth spin singlet. So the azimuth spin wave function or the flavor wave function is anti-symmetric, and then this one must be anti-symmetric, right? Anti-symmetric. This means SL must equal to 0. Okay. From here, we would know the spin of the light quarks inside sigma C and lambda C, and then we will see actually these heavy baryons. They also form into SU3 multiplets. I guess Juan will talk about that in his lectures. So I will just stop the baryon stuff here. Okay. But similarly to the S with heavy light mesons, for heavy quarkonium, you would also have a heavy quark spin multiplates. And similarly to this one, for S wave, you would have eta C and J psi in the same heavy quark spin multiplate. But in this case, the SL for this eta C and J psi, that's because would be different from this one, because eta C and J psi, they are charmonium systems. Both quarks and anti-quark, they are heavy quarks. So the SL, the angular momentum light degrees of freedom, only comes from the orbital angular momentum. Okay, it's simply 0 for them. This is one kind of symmetry. Another kind of symmetry is called heavy quark or flavor symmetry. HQFS. Okay. This one is also simple. So this is symmetry. It's valid for hadrons with only a single heavy quark. Okay, for singly heavy hadrons. Why is that? And that's because for singly heavy hadrons, as I argued before, the momentum scale inside this kind of hadron, right? The momentum that carried away by the gluon from the heavy quark for singly heavy hadrons is always of the order lambda-QCD inside the hadron, right? Because the system is the dynamics of the system is just controlled by confinement, and then confinement scale is lambda-QCD. Okay, so the momentum carried away But this is lambda QCD. Okay, if we put the momentum of the heavy hadron, heavy quark, the initial momentum is p, the final momentum is p prime, and then the momentum of this guy is p minus p prime, right? And then if the momentum change of the heavy quark is p minus p prime, right? This is the momentum change. But what is the velocity change? The velocity change would be the momentum change divided by its mass, right? It's the change of velocity of a heavy quark after emitting a gluon, okay? And then this is of the order of lambda QCD over MQ, okay? Then it's again, if we send the heavy quark mass to infinity, this again vanishes, okay? This means your heavy quark inside the singly heavy hadron basically stays static. Q is static, okay? In this limit. Static means static. It's just sits there without any movement. And then this would mean it does not really matter how heavy that heavy quark is, right? It doesn't really matter whether its mass is 1.5 Jeff, 4.5 Jeff, even 100 kilo. It doesn't really matter. It's just static stuff. Of course, what matters is that it carries some other quantum numbers. For instance, it carries color. Okay, it's a color triplet, right? It's a quark. It's color triplet. So it's a static color source. Okay. Of course, it also carries electric charge, but what we care about is the strong interaction. So I would just write this is a static color source. Okay, and mass does not matter. Mass does not matter. Okay, I use this. So, since the mass does not matter, and then we establish a relation between charm and bottom quarks. Okay? We never talk about the top quarks because the top quark at the lifetime is so short. The width is very large. The width is 2 Jeff, around 2 Jeff. But for a hadron, for a quark to form a hadron, it must interact long enough to form a hadron because the non-productive QCD scale is lambda QCD. This is only 1/10 of the top quark width. So the top quark would already decay before it forms a hadron. So we only talk about charm and bottom. So then we established a relation between charm and bottom. Okay. So as long as we subtract their mass of V, then the charm behaves almost the same as the bottom. But this I want to emphasize. This is only for singly heavy hadrons, right? Singly heavy hadrons. For the heavy quarkonium, then the stuff would be different because for heavy quarkonium, as I argued before, the momentum inside heavy quarkonium is not lambda QCD. It's MQ times V. V is the velocity of a heavy quark inside the hadron. So this means that momentum scale in heavy quarkonium is depending on the heavy quark mass for singly heavy hadrons. Okay. For heavy quarkonium, and then the momentum it depends on mass, and then there is no flavor symmetry for heavy quarkonium. And then this means actually we can learn about the properties, or we can make predictions about bottom hadrons once we know the charm hadrons, or vice versa. We will give some examples later. And then there is generalization of the heavy quark flavor symmetry, which is called heavy anti-quark or diquark symmetry. So sometimes it's written as HADS. Okay. So that's for the kind of systems. Then we consider some baryon for doubly heavy baryon. Okay. Doubly heavy baryon is something you have two heavy quarks and one light quark. But the distance between the two heavy quarks, is basically the inverse of their relative momentum, right? The Q, okay? The relative momentum between the two heavy quarks. And then this is 1 over mq times bq, okay? So, and then if the heavy quarks are very heavy, if they are very heavy, and then this is becomes again a Coulomb-like system, although the Coulomb interaction is not electromagnetic Coulomb interaction, but color Coulomb interaction given by the Van Gogh exchange. But for the very heavy quarks, and then this momentum becomes large, and then this momentum becomes large, and then the distance between the two heavy quarks becomes small. Of course, we're talking about some dimensional quantity, right? This is a dimensional quantity. Whether small or large, we must be justified by comparing another quantity with the same dimension, right? The another quantity is the distance between the light quark and the two heavy quarks, right? This distance is around 1 over mkcd, because the light quark is the dynamics is governed by confinement. So the distance is 1 over mkcd. Now the distance is this one. So as long as the mkcd over this mq, vq is much smaller than 1, and then we can consider these two guys as a point-like system, right? And then QQ becomes point-like, right? You can neglect their distance. Now it becomes point-like. Now it becomes point-like, and then you see it's very heavy, right? And then we just use the same argument here. It doesn't really matter what kind of mass this would have, right? It's a point-like particle, and then it would behave like heavy anti-quark. Why is heavy anti-quark? Because this doubly heavy baryon is a color singlet, doesn't have any color, and the quark is a color anti-triplet, and then the two heavy quarks must be color. The quark is color triplet. The two heavy quarks must be color anti-triplet. Okay. Point-like color anti-triplet 3 bar, okay? Just like the anti-heavy quark, right? So this means we can establish an approximate relation between doubly heavy baryon and anti-heavy meson, okay? Or meson with the anti-heavy quark. That's the heavy quark, heavy anti-quark diquark symmetry. Okay, so now these are the basic concepts. I want to apply them to known particles to see whether reality, the real world, the physical world, really behaves like this. And we can make predictions using this kind of concepts. But of course, first we need to convince ourselves this really works. And then the first example 1, examples. we would consider, for instance, the D star D mass difference and B star B mass difference. Okay. As I said before, the D and D star, they are in the same heavy quark spin multiplet, so their mass difference MD star minus MD must be anti-proportional to the charm quark mass, right? And then this 1 over m mass dimension must be balanced by mass dimension squared. And then what kind of mass dimension what kind of dimensional quantity we can have is just lambda QCD squared, okay, qualitatively. Or we can write it in this way. So it's approximately A divided by MC. A is order lambda QCD squared, okay? Some parameter A. Now, MB star minus MB, okay, would be some parameter over MB. Now we apply the heavy quark flavor symmetry. Because the difference between D star and B star, D and B, are just we replace the charm quark by bottom quark. Or if we really replace charm quark by bottom quark, and then we put B star bar and B bar. But it doesn't really matter, you know what I mean. So and then this means the parameter we would have here is the same parameter, approximately, right? Up to corrections. Relative corrections of order lambda QCD over MC minus lambda QCD over MB. Okay, because we move from charm to bottom. And now we just take a ratio, okay, and then we would get MD star minus MD over MB star minus MB. Now these are the mesons. Approximately equal to MB over MC, right? Of course, you can already put some values to check. But again, we can put some meson masses. The bottom quark mass would be something like B. We can write it this way: MB star plus MB, right? Divided by 2, okay? Minus kind of a parameter. It doesn't really matter. This parameter is of order lambda QCD, okay? So as leading order, we simply neglect that kind of lambda QCD because MB is approximately M capital B is approximately M small b. And then you can also put MD star plus MD divided by 2, okay? Now, what we get is we cancel this 1 over 2. And we would arrive at this very simple relation, MD star squared minus MD squared should be approximately equal to MB star squared minus MB squared. Okay? You can check with PDG. This is very good approximation. That's the application of the heavy quark flavor symmetry. And we can give some other examples. But before I talk about them, let me just first consider some example using heavy quark spin symmetry. We consider example of a heavy quark spin symmetry. That's we focus on p wave heavy hadrons. Okay. So if you check the huge review of particle physics book by the particle data group, you find there are 2 mesons with JP equal to 1 plus charmed mesons. One is called D1 2420. The other one is called D1 2430. Okay. So from the name, you already can tell the masses are very similar to each other, but they have some property that are very different. The masses are similar, but the width, this one is around 30 MeV, around 30 MeV. But this one, the width is around 300 MeV. Of course, there are some problem with this one, but that's complicated. I will not talk about that. But I only want to give some very quantitative understanding of this kind of pattern. Okay. Now, as physicists, we want to understand why this happens, right? So these two guys have the same GP quantum numbers. They have very similar masses. This means they can decay into the same final states, right? They can decay into the same final states. They can decay. The main decay channel would be D star and pi. They cannot decay into D pi, right? Why can't they decay into D pi? That's right. It doesn't conserve angular momentum or parity, right? It cannot satisfy both. So consequently, their main decay channel is D star and pi. This 1 minus and 0 minus, okay? So they decay into the same final states. They have similar phase spaces, right? Because they have similar masses. In principle, we would think their widths would be similar. But there is order of magnitude difference. There must be a reason, okay? The reason is that we can understand it this way. So the parity is positive, okay? This means the orbital angular momentum must be odd. Actually, it must be 1, right? Because 3 you cannot form towards being 0 with quark anti-quark. Okay, it must be p-wave or p-wave mesons if they are really the Q-bar mesons. It must be in p-wave. Okay? But then for p-wave, the good quantum number that we just introduced, the total angular momentum of the last degrees of freedom, we have two different possibilities. Okay, because this one couples with the light quark spin, which is 1/2. We can have either 1/2 or 3/2. Right. Then we put also the parity of the meson here, and then the parity is positive. I just copy from this this parity. Okay, we have these two different possibilities. Now, this one decays into D star and pi. Okay, D star for D star, the D star SL equals to SLP equals to 1/2 minus, right? For the pion, there is no any heavy quark inside pion. And then for pion, SL equals to its spin. And then that's 0 parity, 0 minus, right? This 1/2 plus decays into 1/2 minus and 0 minus. And then this would happen if only the orbital angular momentum between these two hadrons would be D star pi. Okay, the orbital angular momentum inside this D star pi system, this can only be 0, right? So it can only be S wave. Why? It cannot be in P wave, otherwise the parity would not be conserved. It cannot be in D wave, otherwise you cannot. The angular momentum would not be conserved. So the only possibility is S wave. And for this guy, there's a 3/2 plus, and then again it decays into 1/2 minus and 0 minus, right? That's D star, this pi. But for this to happen, we must have additional orbital angular momentum, otherwise the SL would not be conserved. So the orbital angular momentum between D star and pi must be only a single possibility, 2, right? This 2 couples to 0 and 1/2. We can get 3 halves. So it cannot be 1 because otherwise the parity is not conserved. It cannot be 0, otherwise the orbital, this SL would not be conserved. It cannot be 3, 4, all the other possibilities. The only possibility is 2. This is D wave. Okay, it's D wave decay. That's S wave decay. Okay. But then this two-body decay width, d1 to d star pi, right? That is proportional to the amplitude squared, and phase space. Phase space is proportional to the momentum, right? So physically very easy to understand because if you have larger phase space, and then it's easier to decay. So it's then finally mathematically it's proportional to the relative momentum between d star and pi. The angular momentum can easily be computed. Right? All hadron physicists should know the expression for the center of mass momentum, angular momentum. Okay. If you don't know, you need to check and remember that, memorize that. It's a very important expression. And then this means we have different partial waves for the decays, and then they gives you different amplitudes. Okay. For S wave, or for any waves other than S wave, you must have so because angular momentum is something like your momentum across your relative distance, right? So for any non-vanishing orbital angular momentum, your amplitude must depend on some power of momentum. So for S wave, your orbital momentum is vanishes, and then your amplitude can be simply constant, for instance. So it would be the order of p center mass momentum to the power 0. Okay? And for D wave, and then your amplitude would be carries 2 units of momentum because orbital angular momentum that's p cross r, right? You carry 2 units of momentum, and then you would have PCM squared. Okay, and then this means for S wave decay, your S wave decay width is P is order PCM, and then your D wave decay would contain a factor PCM to the 5th, right? Because you have amplitude squared multiplied by the phase space factor, you have power 5th. But how can we compare these two values? Because they don't have the same dimensions. So in order to compare them, we must ask them to have kind of the same dimension. For instance, we would put here some dimensionful quantity to the power of 4, and then to cancel out the dimension to make them having the same dimension. But then what would this lambda be, right? This lambda, qualitatively understanding, would be, we have d star and pi. This could be kind of a momentum scale. This characterize the interaction between d star and pi. For instance, some particle that you can exchange between d star and pi, the mass of that particle. And then that could be, for instance, the light vector mass on mass. And then, for instance, rho or omega, this kind of stuff. And then here, we would write this as m rho to the 4th. And then this d wave decay width over S wave decay width would be approximately suppressed by P, the momentum, over this m rho to the power of 4. Okay? And you can check this momentum is 300-400 math. The rho mass on mass is how large? 770, right? So it's basically 1/2 to the power of 4. It's a very small number. So it gives you the desired suppression. A question? So this would tell us that to a very good approximation, this D1 2420 is to a very good approximation a heavy quark mass, the charm meson with SLP equal to 3 half plus. Okay. Yeah. Well, it cannot be other lighter scales, or the of course it can be. They can exchange heavier particles, but I want to put the lightest one to compare, to have a comparison. D star and pi, they cannot exchange pi, so they cannot exchange pion. So it says just kind of hadronic scale. It's normally you just put 1 Jeff. And here you have very good reason. This should be approximately the light vector meson mass, that kind of scale. Around 1 Jeff, 800 MeV, it's approximately 1 Jeff. Okay, so that's what we can conclude. Okay, and of course this one has a strange partner, which is D space 1 or 25 or 36. Okay, and SA equals to 3 halves. And then you will find this multiplate, this heavy quark spin multiplate, contains, in addition to this D1 2420, it must contain another meson with the spin 2, right? This 3 halves couples with 1 half for the heavy quark spin, gives you spin 2 particle. That's D2 2460. And then this D2 2460, this decays in D wave to D pi. It also decays in D wave to D star pi. And you can derive relations between the width of this one and that one. You will see experimental observation is approximately satisfied by the relation that you can derive for the width using the heavy quark spin symmetry. And this one, you have DS1 24, 25, 36, and then you have DS2 25, 73. Okay, it's another multiplate, the charm strange meson multiplate. But then, if you check PVG, for instance, okay, you find, in addition to DS1 25, 36, you have another particle, DS1 2460. Okay. That was reported in 2003. It's funny. So that was reported in 2003 by Clio. Well, but actually, the signal was already there in Barbara's paper, which reported DS0 star 2317 in the same year, a few months earlier than the Clio paper. If you check their paper, you see very clear signal around 2.46 GeV. But at that time, they did not dare to claim observation of 2 new particles in the same paper. But they already observed this one, right? So there's very important observations. Basically, these observations started all this new the discussions of this kind of exotic hadrons containing heavy quarks. Okay, this 2003. So this JP equals to, you see this the name DS star, DS0 star. The JP equals to 0 plus Why is there a star? The particles names with a star means these are particles with a natural parity. Natural parity means the parity is simply -1 to the power of their spin. Okay? So this is a scalar particle. Their name is 0 star. And then this okay. If I simply follow exactly this rule, I should put a star here. Star here. Okay. Sometimes you see some papers that doesn't neglect this stuff, but it's not essential stuff. And then this JP for this one is 1 plus. But the strange, the weird observations was that although this kind of observations, they agree pretty well with predictions, with the theoretical predictions, for instance, from constituent and quark model. The most famous one is the Godfrey-Esker quark model. Godfrey-Esker quark model in 1985. But these two, actually, their masses, as indicated by the numbers inside the parentheses, they are much lower than the Godfrey-Esker quark model predictions. For instance, this one, the mass is lower than the quark model prediction for CS bar 0 plus meson by more than 150 MeV. It's a sizable difference, right? And this one is lower than the lowest CS bar 1 plus quark model prediction by 80, 90 MeV. So both observations led to masses much lower than one would naively expect from quark model for CS bar mesons. And then this just brought into interest to the theoreticians. Then many different models were proposed. And then lattice QCD calculations were also done. And nowadays there are still ongoing investigations of these states. But without any detailed understanding of this, as a theoretician or as an experimentalist, we can already observe or predict their bottom partners, right? If we can predict their bottom partners, and then if you work in, for instance, in RC, and you can try to search for them, right? The RC, you have enough energy, although they might not be easy to find the evidence, but we can make prediction of their bottom partners from heavy quark flavor symmetry, no matter what kind of internal structure they have, right? It doesn't really matter whether they are teraquark quark states or hadronic molecules. It doesn't matter. You don't care about what theoreticians like me are seeing, but you can already predict their bottom partners, which is really independent of all these theoretical models or theoretical pictures, using heavy quark flavor symmetry, which is model independent prediction. And then how would you predict this, right? So the prediction would be simply you can understand this. The difference would be simply you replace the chum quark by the bottom quark. You just plus the bottom and chum quark mass difference to their masses, right? Then you get your bottom quark, the bottom prediction for them bottom partners. But then we can write this down very easily in a few minutes. So yeah, then 3 minutes, then we can do this prediction. So the prediction we can start from this, right? So this DS1 and DS0, no matter what kind of model they are, always they are assumed to be in the same spin multiplate. Okay, the same spin multiplate. And then they have an average mass, which is independent of the spin-dependent interaction. Then we can define some average mass for the chump mesons, and then that would be the spin average mass. This is spin 0, that's spin 1, and then in total there are 4 of them, right? The spin 0 and spin 1 has 3 components, right? Then M ds0 star plus 3 MD mass 1, okay? you have this kind of average. And then similarly, you can define similar stuff for the bottom part. Okay, you just replace D by B. Okay, and then of course you can know. Okay, you know this one would be the M average C plus MB minus MC, right? And this one you can approximate this by, for instance, the spin average mass of BS. Average BS. That means B sub S and B sub S star spin average mass minus spin average mass of DS. Okay, and then you just put the masses that you can check from PDG. You get this value. But then the mass of B0, B sub S0 star, okay, would be the average mass of this one we already take from here, plus the now we consider more the half-fine splitting, the more finer structure. Then we would use the DS0 star mass minus the average mass in the charm sector, and then multiplied by MC over MB, right? Why is this? Because this is half-fine splitting. This is spin-dependent interaction, which is anti-proportional to the heavy quark mass, right? So we use this effect, and then we use heavy quark flavor symmetry to treat this one from the charm sector into the bottom sector, and then multiply by this ratio, and then we would get the difference into the bottom sector. And then you put all the values that you have very quickly. You get something like 1.71 Jeff. Okay. This one is similarly B sub S1. Okay, approximate average B plus D sub S1 minus M average C MC over MB. And then you put all the masses, you would approximately get something like this. Okay, so that's within 3 minutes we finished this prediction. And related to KCD, they did the calculation. What they found is really some number like this. Right? Although we did in a few minutes, they probably did in a few months. So they find numbers consistent with this. Okay, good. So we finished for today. Thank you.